We introduced the Kelvin temperature scale at the end of our last lecture. We did this by considering a heat engine. The thermal efficiency of a heat engine is the power output, the goal of the device, divided by the heat transfer coming into the device from the high temperature reservoir. In the notes, this is actually reversed. I apologize. I've now corrected it. It's W dot over Q dot, not the reciprocal of that. The power output can be represented as Qin minus Q out with an energy balance, and if you substitute, now we can come up with an expression for the thermal efficiency only in terms of the two heat transfers. So this is the heat transfer in from the high temperature reservoir. This is the discharge out to the low temperature reservoir. Right, so this Q out is the part of Qin that does not contribute to work. So this is effectively the wasted part. So 1 minus the wasted part is the thermal efficiency. For the reversible case then, all we need to do is consider these Q's to be for any conceptualized reversible process, Q out over Qin for a reversible process, any reversible process here. Then everything on the right hand side of the equation is now referencing a reversible situation, so this would be the reversible thermal efficiency. So the highest possible performance according to the first Carnot corollary. This performance, then, the highest performance, is only going to depend on TH and TL. It doesn't depend on any of the particulars of how the process works, only the two temperatures of the reservoirs TH and TL. So recognizing that, let's move this constant over to the other side. We now have a relationship between the reversible heat transfers to something that should be only a function of the two temperatures. And so this is where some research begins to figure out what must this function be for this conceptualized reversible case. So some science and some history and research has gone into that. There are observations that that must be also a separable function, meaning that it needs to be a function of TH times a function of TL. Lord Kelvin proposed that we keep this as simple as possible, and so he said let's consider TL over TH. We'll just take that ratio, and it turns out this works, and this is the basis of the Kelvin temperature scale, the absolute temperature scale. So this only works if you use Kelvin or degrees Rankine for these temperatures. And so without kind of proof or an in-depth discussion of the science behind this, you are okay to accept this and use this at any point, take it at face value or take it as correct anytime you're working through an analysis. So what Lord Kelvin gave us, let's just go down, skip some of the theoretical discussion. We can save that. You guys can read that on your own, and maybe we can talk about that. We already have a little bit in our Zoom sessions. What Lord Kelvin has given us, it actually applies equally to refrigeration cycles and power cycles. For the power cycle, QH coming in, QL going out, and then for a refrigeration cycle, QL coming in and QH going out on the other side. The ratio of these two in both cases is just equal to the temperature ratio as long as these are in absolute temperatures. So notice that the numerator is associated with TL in both cases, right? This is QL out and QL in, so this is the numerator associated with the heat transfer interacting with the lower temperature reservoir. The denominator is that with the high temperature reservoir. So the in and the out is not so important here. You need to recognize that the numerator TL is associated with the heat transfer to that particular reservoir, and the same thing for the denominator. And of course you can take the reciprocal of this and it also applies. Right? You could say QH over QL is equal to TH over TL. That would also work. But this is equally valid for whichever device we're looking at. In the reversible case, the conceptualized reversible case, these heat transfer ratios is just equal to TL over TH. One more observation is if these are devices operating steadily in a cycle, then these could be Q dot in all situations. So Q dot L in and Q dot H out. And this still applies. It's still TL over TH. Notice that that will still be a dimensionless ratio on both sides of the equation. So now let's take this information about the reversible case and the heat transfer and look at what's called a Carnot engine is a reversible heat engine. For a reversible heat engine, right, the thermal efficiency, well, for any heat engine is 1 minus QL out over QN, like we just discussed. For the reversible case, just replace that ratio with this reversible situation, which happens to be TL over TH. So just make the substitution. The thermal efficiency for the reversible, or it's called the Carnot efficiency, thermal efficiency for a reversible heat engine is 1 minus TL over TH. And as long as these are in absolute temperatures, either in K or degrees Rankine, you'll get the same efficiency. So now we have a means to evaluate the second law. Check the thermal efficiency for any device and compare that to the reversible case. Right? If the thermal efficiency of the device is less than the reversible case, then it is theoretically irreversible and a possible real device. Doesn't guarantee, but at least it doesn't violate at least the second law theoretically. So this we would say satisfies the second law. It's a physically, potentially real device, so a realizable device, and we'd call that irreversible. If we had an answer that said our thermal efficiency was equal to the reversible case, that's also not a physically possible device. However, that is our conceptual limit. So we'll recognize that as, hey, this is a totally reversible heat engine. If it's greater than that, now you have a device that's absolutely impossible. It theoretically violates the second law, so we would just call that an impossible device, and you really shouldn't waste your time trying to create something that is going to break the second law of thermodynamics, although that doesn't stop people from trying. So take a look at this formula up here. Then this kind of tells us the best, so this is the upper bound that we can achieve on the thermal efficiency, and it's a function of TL and TH. So let's consider how this function varies, how it depends on TL and TH. So notice that as TH and TL come together, so our temperature difference is reduced, this approaches 1. And so we get a thermal efficiency of 0. So we actually cannot produce any energy if we don't have a temperature difference. That seems logical considering our previous discussion about the second law. And then also then if the opposite case is true, so what if our TH and our TL become farther and farther apart? You increase that, then you get a better, a larger and larger reversible efficiency. So in that situation, it is kind of easier to create an efficient device. There's more room, I guess, to create devices that are irreversible and still have a respectable performance. Okay, so let's work some examples now. That's the same problem. Let's consider a power cycle. Operates between a high temperature reservoir at 1727 degrees C. The low temperature reservoir is at 127. And then it gives us several different situations for a heat engine that's operating between those two temperature reservoirs, and it wants us to decide for each one of those, is it an irreversible, so possible, or impossible, or the reversible case. Okay, so let's make a little schematic. This is TH and then TL, and there's a heat engine. Right, so energy is brought in from, I'll put a little subscript H, and I'll also put the word in there to recognize its direction. It's coming in. This can be a dot or not. Either consider analysis with all heat transfer rates or not. So let's just not mix them. So let's say, since they're giving us Q's up above, I'm going to call it Q here. A Q discharge will be Q. I did it again. I did a dot. I like to put the dot apparently. Q L out. It's discharging here. And the difference between those is the W net that we're able to produce. The high temperature reservoir is at 1727 degrees C. It needs to be in absolute, so immediately convert those before you forget and make that mistake. Add 273 to that and you get 2000 K. For T, the lower temperature is 127 degrees C. Add 273 to that and we get another nice round number, 400 K. And so we could kind of recognize that the reversible efficiency for this heat engine, remember that's 1 minus QL out over QH in. For the reversible case, if I have the reversible here, then I have reversible distinction here. This is 1 minus TL over TH. So we can make a substitution. Our reversible efficiency in this case is 1 minus 400K divided by 200K, so 0.8. So 80% efficiency is the highest efficiency that could ever be achieved for any heat engine operating between these two reservoirs. Okay, so let's consider A. In part A, we say the heat transfer is equal to 1200 kilojoules while we're producing work at 1020 kilojoules. Okay, so let's assess the efficiency of what's being proposed for part A. Right, the efficiency is going to be equal to W net divided by Q in. Okay, so 1020 divided by 1200 kilojoules on each of those. Let's not forget our units, we'll cancel. So this comes out to be 0.85. Alright, so 0.85 is greater than the 0.8 for the reversible case. Alright, so the thermal efficiency is greater than the thermal efficiency for the reversible case. So our conclusion is that this is impossible. This violates the second law of thermodynamics. Alright, so these problems are quite easy, right, when it comes down to the calculations that are necessary. I need you guys to communicate all of this. Don't just look at that and in your head do the calculation. Oh yeah, that's going to be 0.85 greater than 0.8, therefore it's impossible. If you just tell me it's impossible, that answer is not going to be good enough. You have to substantiate your answer and tell me why it's impossible. These problems are easy, so at least focus on the communication for these. Okay, so now let's look at part B. Part B says QH is equal to 1200 kilojoules again, but this time it's going to give us a Q, this is in, a QL out is equal to 240 kilojoules. The thermal efficiency again is W net over QHN, and the other tool we have to work with is an energy balance. The way I would write an energy balance is I would look at the arrows. Qn is equal to W net plus Q out, right? This coming in is split between these two going out, so I would write QHN is equal to W net plus QL out. Alright, so we can solve this for W net is going to be equal to QH in minus QL out. So of this 1200, everything that's not going out through this 240. Alright, so this comes out to be 960 kilojoules. So now we can use this number and go back and calculate the efficiency. So the efficiency is now equal to 960 kilojoules divided by what's coming in is 1200 kilojoules. So this is an improvement compared to above. This comes out to be 0.8. Right, so the thermal efficiency now we have found is exactly equal to the Carnot efficiency, or the reversible efficiency. So we would call this reversible. Still conceptual, right? Not a realizable device, but this is the upper limit, theoretical limit to help the engineer during the design process. Okay, so now let's look at part C. Actually, let's still keep our graphic there. So part C says W net is equal to 1400 kilojoules. QL out is equal to 600 kilojoules. Okay. Let's look at our energy balance again. Q in has got to provide the net work out plus the QL out. Both of those, so now this gives me, use these two numbers, combine those together, I get 2000 kilojoules of energy coming in, and now I can use this number to calculate the efficiency again. So this will be W net divided by QHN. For this case I get 1400 kilojoules divided by 2000 kilojoules, so 0.7. So that 0.7 is less than the 0.8 for the reversible case. Alright, so the efficiency is less than the reversible efficiency. Implies that this is a possible, so irreversible device. So I will call this theoretically possible. So it does not violate the second law. Continuing on, case D, they just give you the efficiency is 0.4. So nothing really to evaluate there, just recognize that that is less than the reversible case. Right? Again, this would be irreversible. So theoretically possible. For the last case, they give it to us in terms of powers, but that's fine. So W dot net is equal to 1400 kilowatts. They tell us that Q dot L out is equal to 400 kilowatts, and then also that Q dot H in is 2000 kilowatts. So they give us all three so that we can use that to check the first law to begin with. Let's check the first law. First law would say that Q dot H in is equal to W net plus QL out. Those are all dots there. Alright, so this one they're claiming that that one is 2000 kilowatts. If you add these two together, 400 plus 1400, you get 1800 kilowatts. Alright, so these are not equal. This process violates the first law. Process violates the first law. Therefore, this process is impossible. Doesn't matter what your analysis says about the second law. If any physical law is violated, the device is not possible. But let's go ahead and, for entertainment's sake, go ahead and calculate or evaluate the second law. For the second law, we'll use the thermal efficiency again, W dot out divided by QHN. If we use the numbers they give us, so not attempting to make some correction for the first law, this will give us 1400 kilowatts divided by 2000 kilowatts, which is 0.7 less than the reversible case. Right, so this doesn't violate the second law. So we're good on the second law, but that's okay. A violation in either makes this impossible. Violations of the first, and put an or there, or the second law, imply that this is impossible. Okay, let's look at another example. Power cycle. Again, the power cycle operates between a reservoir at temperature T and a low temperature reservoir at 280 K. At steady state, the cycle develops 40 kilowatts of power while rejecting 1000 kilojoules per minute. So recognize that detail of the units to consider a heat transfer to the cold reservoir. Determine the minimum theoretical value for the temperature. And it wants that in K. So this is, first of all, a power cycle. Let's draw a power cycle to keep this organized. We have a low temperature and we have a high temperature. The high temperature they're just calling T, so I'm just going to call it T as well. I just put HE here for heat engine. Energy comes in. Some of that produces some power and some of it gets discharged. So W dot out is equal to 40 kilowatts. And then Q dot L out, they give us that as well. They say there's 1000. This is equal to 1000 kilojoules per minute. I would immediately convert that to 1000 divided by, there's 60 seconds, right, in every minute. Kilojoules per second. So that ends up being 16.67 kilowatts. For QL out, WL out is 40 kilowatts. So we could do an energy balance to figure out what must be that Q coming in as well. They're asking us to find the theoretical minimum. Theoretical minimum for this TH. If you remember, we recognize that the thermal efficiency, the reversible thermal efficiency, goes down the closer these temperatures are together. So the closer these temperatures are, the lower this T high is, the more difficult it's going to be to produce or achieve this efficiency. So this is QHN, right, which must be equal to Q dot out plus the QL out. Okay, so let's go ahead and write down the equations we're going to use to analyze this. W dot out is the desired output over the required input is QHN. And we already wrote down our energy balance. QHN is equal to W dot out plus QL out. We have that as an energy balance. We could go ahead and compute what this is going to be equal to. 40 plus the 16, so this is what, 56.67 kilowatts must be what's coming in. let's see. So now we need to figure out what is the theoretical minimum. For the theoretical minimum, we're going to keep lowering this temperature until the thermal efficiency that's achieved here is equal to the reversible case. And without going through a derivation, you'll probably remember that the reversible case is 1 minus TL over TH. Right, so I'm just going to call that T in this case. So let's go ahead and put minimal right there. T minimal occurs when we set eta to the reversible case. Okay, so this efficiency here is going to be W dot out over Q dot HN. Comes out to be the 40 kilowatts divided by the 56.67 kilowatts. This is 0.706, so 70.6%. We're going to set that equal to our reversible efficiency there. This temperature TL is actually equal to 280 K. I should have added that up above, right? TL. It's already in absolute temperature. That's supposed to be an L, not a 2. TL there. Alright, so now we can use this equation, put our 0.706 there, use this equation to solve for T minimum. T minimum is going to be equal, if you do some algebra, this is TL divided by 1 minus eta. So 280K divided by 1 minus 0.706. Don't be lazy, keep the 3 decimal places of accuracy there. This comes out to be 952K. That's the minimum possible temperature that will allow that process to occur as they have it proposed. So in fact, the second law then would suggest that T has to be greater than or equal to 952 for this process to occur. I'm not going to require that you memorize this equation, the reversible case. But I'm also not going to give you this equation either. Of course, it's going to be open book, so I guess you can go look up those equations. I have a tendency to not want to memorize these equations, and it's too easy to start with the concept of efficiency being W out over Q in. Right, make a substitution with an energy balance to put this in terms of just the heat transfers, and when you finally get a QL out over a QL in ratio, replace that with TL over TH. So it's not too difficult to get to this if you don't remember it, if you just know the concepts. Okay, so those were examples involving heat engines. Let's consider refrigeration cycles and heat pumps as well. So here's our general schematic for that. Low temperature reservoir, high temperature reservoir. We have some clever refrigeration device that takes power input or work. Right, these could all be dots or not. It takes work input and is able to achieve a heat transfer being drawn out of the low temperature location and discharged to a high temperature location. We had a coefficient of performance, right, that is defined for a refrigeration cycle. The goal is to produce this. This is the goal for refrigeration. Goal for refrigeration. If it's a heat pump, then this becomes the goal. Goal for a heat pump. So we've done this before. I'm not going to go through the energy balance. The derivation for these simple little cycles. This is what this textbook calls beta. You don't need the sub R for a refrigeration cycle. If you take beta being defined as QL divided by W net N and then do an energy balance to substitute for W net N in terms of heat transfer, this is that same expression. This is equivalent to QL N divided by W net, desired output over required input. Then for the reversible case, right, I'll just need to recognize that this ratio of heat transfer needs to be, for the reversible case, it's H over L, so it'll be TH over TL here. So this is the coefficient of performance, beta, for a refrigerator for the reversible case. Okay, we can do the same thing for a heat pump. This textbook doesn't use beta for the coefficient of performance for a heat pump. It uses gamma, so I need to change that, so you can change that in your notes. So gamma, reversible, so this represents the Q out, QH out divided by WN, the goal, and then make a substitution to replace WN to end up with an expression with a ratio of the heat transfer. So you've seen that before. This is QL over QH, reversible now, that can be replaced with TL over TH. Right, again, the numerator matches TL, QL. Up here it's TH, QH. And same with the denominator. So you can use this expression for gamma reversible. Also recognize that, look at the denominator. The denominator here is actually the coefficient, the efficiency if this were to be a heat engine operating. So for a heat pump, if you want to know the coefficient of performance, you can take the reciprocal of treating it as a heat engine. So it's 1 over eta. And then taking a look at the formula up there, notice that as T approaches TL, as that difference gets smaller and smaller and smaller, those ratios become 1. Notice that both of these expressions approach infinity. And so as the temperature difference comes together, there actually is no limit on the performance according to our theoretical analysis that we've done here. You can theoretically have a higher and higher and higher performance. But notice that this is the case for a heat pump or a refrigerator. The idea is that you have to promote the heat transfer. So that what this is saying is that it's very, very easy to promote heat transfer from a low temperature to a high temperature when those temperatures are closer together, until eventually, if there is no temperature difference, then we can't put a limit theoretically on the performance. So a refrigerator or the air conditioner in your home works best when the temperature outside is the same as the temperature inside. So it works best when literally you don't need it. So it doesn't have that much of a temperature difference to work against. Larger delta T reduces the performance of the cycle. If it has a bigger load on it, its performance is going to be reduced. So it kind of makes sense. Let's work another example. An inventor claims to have a refrigerator that maintains a cold space at 35 degrees Fahrenheit while operating in a room. The room temperature is 75 degrees Fahrenheit, and he claims that he can achieve this with a coefficient of performance of 13.5. Remember that both beta and gamma are not restricted to be less than 1, like eta is for a heat engine. So the coefficient of performance is 13.5. So is his claim reasonable? So the first question will be, well, what does this mean when it's asking, is the claim reasonable? Basically, we're going to check the first and the second laws, what that means. Check the first law and check the second law. It's real easy to do that, and at least use that to make some judgment as to whether or not this is possible. Okay, so let's see. Let's get this organized. We have a low temperature and a high temperature. The high temperature TH is 75 degrees Fahrenheit. The low temperature is 35 degrees Fahrenheit. I would convert these right away. So you got to add 459.7 to these, or 459 460, sorry, do 460. This becomes 534 Rankine, and this becomes 494 Rankine. So this is a refrigeration cycle, so I'm going to draw my circular refrigerator. Energy is coming out of the low temperature reservoir being discharged to the high temperature reservoir. So we have L for the low temperature reservoir, and that's coming in. This will be Q dot H, and that's going out, and then our power has to be coming in. W dot, I'm going to call that W dot N so that that can be a positive number. So they're claiming that beta is equal to 13.5. Okay, so let's think about the coefficient of performance. Let's just write down our kind of analysis tools, definition of the coefficient of performance. In this case, the goal for a refrigerator is to pull energy out of our cold reservoir so that we can keep that cold. QLN is the goal. It's costing us some power in. This is going to be power input to a compressor. W dot N is coming in. So then let's do a first law. This comes in, that comes in. Those have to total to be this Q going out on the other side. So I would put W dot N plus QLN is equal to, Q dot H out. Okay, so this claim actually doesn't give us any numbers really to use to check the first law. So I would say the first law is not even challenged by the claim above. First law not challenged. There's nothing really to check, right? So I would put no claims on W dot N, QLN, and QH out. You don't have any numbers that you can go and check that. So now let's move on to the second law. Then to check the second law, the question then becomes, is beta less than or equal to the reversible case? And we're just going to compare to that. Okay, so we need to find beta reversible. So you could just remember the equation and write that down in terms of TL and TH. I'm going to go through a quick little derivation. Beta, remember, is QL over W dot N QLN. Do an energy balance. This will be Q dot LN. Replace this one with our energy balance up above. Take that to the other side. So this becomes QH out minus QLN. And now let's factor out QLN on the top and out of the denominator and let that cancel. This is equivalently equal to 1 over QH out divided by QLN minus 1. So for the reversible case, we'll just replace that with TH over TL. So beta reversible is equal to 1 divided by TH over TL minus 1. Or you can just go and look up that formula or remember it. Okay, so we can now substitute in numbers. 1 divided by TH is 534 degrees Rankine divided by 494 degrees Rankine minus 1. This comes out to be 12.35. This has to be degrees Rankine here, or you can convert it to K and you'll actually get the same answer. Our conclusion then finally from this, we have to communicate an answer and then a reason for the answer. Beta is equal to 12.35. Right, that's actually greater than reversible. Beta is equal to I'm reading things backwards now. My apologies. Beta is equal to 13.5 is what's claimed. That's actually greater than the beta reversible that we just came up with, which is 12.35. Alright, so the beta claim greater than beta reversible is impossible. This claim violates second law. This is an impossible device. Okay, so I think we accomplished an evaluation of the claim. The claim is not reasonable. Maybe we should answer it exactly the way it asks. Is his claim reasonable? Not reasonable. Okay, I have another example to work, and this will be our last example for this lecture, I think. Yes. Well, we'll see. It started. We were 40 minutes into this. We'll see how many more of these we're going to work. Okay, so this one is a heat pump. It's hoped to maintain the heated space at 72 degrees Fahrenheit, so like the inside of your home, to make it nice and comfortable on particularly a cold day. The compressor motor can deliver a maximum of 7.5 horsepower. So that's the maximum amount of power that can be delivered to try to achieve or maintain that cooled space. And then they give us some more information. They say on a day when the outdoor temperature is 10 degrees Fahrenheit, so it's a fairly cold day, the heating demand is 100,000 BTUs per hour. Can this pump possibly maintain the 72 degrees Fahrenheit space? So let's consider that question first. So we have, keeping this organized, two temperature reservoirs, TL, and this one is TH. We have a heat pump this time instead of a heat engine, heat pump, taking energy out, QL in, out of this space, so into the heat pump, delivering QH out to the high temperature reservoir, and this is costing us some work coming into our device. This work in, they're telling us, is restricted. It has to be less than or equal to 7.5 horsepower. And then they tell us that the heated space is equal to 72 degrees Fahrenheit. So let's convert that to 531 degrees Rankine. And then this cold temperature reservoir is the temperature outside. This would be the temperature inside. We're trying to maintain the 72. This would be the cold temperature outside. So this varies depending on part A, B, or C. So this, let's go ahead and write down maximum possible input power. Okay, so considering part A, they're going to tell us that TL is equal to 10 degrees Fahrenheit. Convert that immediately to 469 Rankine. And then they're telling us that, they're telling us that the heating demand is 100,000 BTUs per hour. So the heating demand, okay, so that's how much heat has to be provided to this space in order to maintain that 72. So that means there's 100,000 BTUs per hour leaking out of our house out to our cold space. Alright, so that heating demand they're giving us is QH out. QH out is equal to 100,000 BTUs per hour. Okay, so can this pump work for this? There's a couple of ways that we can go about this. One is that we could theorize and calculate what is the work required and then compare that to this efficiency, or we could say, let me just take this maximum, or evaluate the maximum efficiency and calculate what the efficiency of this device is. What I did, so let's go ahead and write down, this is for a heat pump, so let's use gamma is equal to Q dot H out, that's our goal, divided by W dot N, what's being delivered. We can convert that to a QH out with an energy balance. This Q that's coming in is actually QH out minus Q LN. Right, the difference between those two is this power from an energy balance, right? Factor out QH, and we'll end up with a 1 divided by 1 minus Q dot L over Q dot H. This is H out, L is in, and those are dots. Okay, so all I did was work to get this expression for the performance expressed in terms of a ratio, and now I can substitute TL over TH to get the maximum or the reversible performance, 1 over 1 minus TL over TH. So that's going to equal 8.56. Substitute in a temperature of TL 469 over 531. Alright, that's going to be 469 over 531. Substitute those two temperatures, so that's the maximum possible performance that can be achieved. So we could use this number to calculate the minimum amount of work required. The best performance would be associated with the minimal amount of work. So W dot N was going to be equal to Q out divided by gamma, using our expression here. Alright, so the minimal, this would imply that W dot, let's call it minimal, would be equal to Q dot H out divided by, put gamma reversible here, or the maximum value of gamma would give us the minimum value of work over here. Okay, so we can substitute, what do we have, 100,000 BTUs per hour divided by our 8.56. This comes out to equal 11,676.08 BTUs per hour. If you convert that to horsepower, it's 4.588 horsepower. Okay, so our pump can achieve that. Alright, so I'll put as an answer, since 7.5 horsepower maximum that we have is greater than this kind of minimum value, you have to apply at least this, then yes, the pump may work. Let's put it that way. The pump may work. In fact, there's a lot of extra power there available, right? There's another 2 horsepower, 3 horsepower actually, that could be used to overcome any inefficiencies or irreversibilities of the system. So that's probably a very likely useful or successful cycle. Okay, so now let's look at part B. Says we're going to consider a different day. Consider a day when the outdoor temperature has now dropped to 10 degrees Fahrenheit. It was colder outside, and now the heating demand is increased. It's twice as high. It's up to 200,000 BTUs per hour. Seems logical. If it's colder outside, there's going to be more heat transfer from the inside of your house to the outside, because we know heat transfer is proportional to the temperature difference. So in this situation, repeat that analysis. Can this same pump possibly work? And so there's going to be a larger delta T, so the maximum performance is going to be reduced, so the pump is going to be challenged more because of that. And then also we have a higher load on the pump, so it's going to be challenged because of that. So it may not work in part B. So considering part B, we're going to say TL is now equal to minus 10 degrees Fahrenheit. Convert that to degrees Rankine right away. 449 degrees Rankine. And now our QH load, or QH out, is equal to 200,000 BTUs per hour. Gamma max is different now. It's still 1 over 1 minus TL over TH. But now I have a different temperature to use for TL, 449. This comes out to be 6.4756. So a lower number, right? Larger temperature difference, the harder it is to cause the heat transfer to occur. The minimal amount of power required to achieve this would be Q, our load, out, divided by this gamma reversible. Oh, I called it max up here. It's the same thing. It is max, right? I've called it max in previous classes. So this comes out to be 200,000 BTUs per hour divided by that 6.4756. So in this case, 30,085 BTUs per hour. In terms of horsepower, this is 12.14 horsepower. So larger than the 7.5 horsepower we have available. Since the given max, 7.5 horsepower, is less than 12 horsepower that is required up above, no, the pump will not suffice, is the answer. No, the pump will not suffice. It probably will be able to achieve some warmer temperature than 10 degrees Fahrenheit inside, but it will not be the 72 on the inside. Now let's go to problem C. Assuming a constant heating demand of 100. So we're going back to the case A situation on the load. Determine the minimum outdoor temperature in degrees Fahrenheit for which the pump would work. Okay, so in this one we're going to assume that that delta T is not changing the load. In actuality, it will change the load if we were considering a building. But this, for theoretical purposes, we're going to keep the load the same, so that's going to be a constant. So for part C, QH out dot is equal to 100,000 BTUs per hour. And we want to find the maximum operation of the pump. So we're going to take gamma is equal to, we're going to say our W dot N is equal to the maximum value. So we're going to operate at our 7.5 horsepower. So then the performance would be equal to, performance is Q H out divided by the power N. So 100,000 BTUs per hour divided by the 7.5 horsepower. So we're going to have to do some units conversion here, right? So units conversion. I think you guys can handle the units conversion. My calculations give me 5.239 for the performance coefficient in this case. Okay, so now what we're going to consider that if this thing is reversible, that would give us the minimum possible temperature TL. If reversible, that would imply TL is equal to, implies a minimum. Alright, so we're going to say gamma is equal to gamma reversible, so that is 1 divided by 1 minus TL over TH. And then we're going to solve for TL. Solve for TL. If you do the algebra for that, you'll get TL is equal to 1 minus 1 over the efficiency. Oh, sorry, not efficiency, gamma reversible times TH. This comes out to be 429.6 degrees Rankine. So minus 29.4 degrees Fahrenheit. The theoretical minimum that would allow this pump to work, to be able to successfully maintain 72 degrees Fahrenheit inside when it's that cold outside, so long as the heating demand stays at 100,000 BTUs per hour. And this would not allow for irreversibilities, and so the real answer is that it would be higher than that number. That is the minimal possible value, right? Minimal TL. So at the theoretical limit. Okay, there are a couple more examples that we could work. I'm going to stop this lecture here at just under an hour, and I will, you know what, I'm going to save the rest of those examples for you guys to work, and we will talk about them in the Zoom session. See you guys tomorrow.